Okay, the third part, before we go to the detail of the viscosity, I would like to show you some clip from YouTube about property of the non-Newtonian fluid. Okay.
Interesting topic of Newtonian and non-Newtonian fluids. A classic Newtonian fluid is water. Water has a very predictable viscosity and will always flow predictably regardless of the forces acting on it. Newtonian fluids also have predictable viscosity changes in response to temperature and pressure changes. To investigate the properties of Newtonian fluids experimentally, let's start with some warm honey. As you can see here, warm honey flows easily, and it will easily flow around objects, such as this ruler. Placing a force on the honey has no effect on its viscosity. Even if we place a large force on it with a hammer, the honey predictably flows around the hammer. If we try the same thing with cold honey, we see, as you would expect, the honey is more viscous. That is, it flows slower. But when we test it with the ruler, we see it behaves much like the warm honey. It's the same when using the hammer. Applying a force has no effect on the viscosity. Honey, whether it's warm or cold, is a good example of a Newtonian fluid. Let's try a different fluid. We'll perform the same test with cornstarch solution. When you pour this solution, it appears to behave much the same way as the honey. When you place a ruler into it slowly, the fluid flows around the ruler. However, when you attempt to force the ruler into the fluid instantly becomes more viscous. Hammering the fluid with even more force produces even more resistance to flow. Because a cornstarch solution's viscosity changes with an applied force, it is a non-Newtonian fluid. Unlike a Newtonian fluid, applying forces to this non-Newtonian fluid causes its particles to behave more like a solid. This makes the behavior of non-Newtonian fluids very strange. As you can see here, even though cornstarch solution flows when emptied from a bucket, you can't break its surface even when using a sledgehammer. You can even jump on and off a cornstarch solution. Just remember, don't stand on it, as you will eventually sink. So in summary, non-Newtonian fluids have unpredictable responses to applied forces. With applied forces, they become more viscous, such as cornstarch, or less viscous, like ketchup. What other fluids might you suspect to be non-Newtonian fluids? Try your own fluid experiments to find out.
Okay, that is the clip about the cornstarch. So the next, if we look at the number of the dynamic viscosity, for example, fresh water. So this is viscosity is about 10 power minus 3. Okay, the seawater is a bit higher. For mercury is higher than the fresh water, and engine oil. This is very small compared to just 10 power minus 1. And for the engine oil, they use the symbol SAE 110 or SAE 30 oil. So this one is they use from the Sebo measurement to measure the viscosity. So SAE 10 is mean that it takes 20 seconds to passing through the instrument, and SAE 30 is take a 60 minutes, 60 seconds. So this is show the is we call the Sable's viscous meter. They put some tube in the constant temperature bath, okay, and the volume of this bottle is 60 centimeter, 6 cubic centimeter fixed, and they put the fluid inside, and this the outlet diameter is D is fixed, and for the weight of the fluid is equal to volume times rho g, and for the outlet area is pi over d square, pi over 4d square, and they measure the viscosity using the W divided by A, which is a constant, and time the delta T. So it means if the delta T is increased, it means the viscosity increased, okay. Another thing about the SAE is come from the Society of the Automobile Engineer of America is standard. A device for measuring the viscosity. We call the Sable viscous meter. Okay. The other property of the liquid and gas, the difference between liquid and gas. For the viscosity for liquid is decreased with the high temperature, but for gas it increased with the high temperature. That show in this figure show that for liquid, gasoline, oil, and water, once the temperature increase, the viscosity decrease. But for air and hydrogen, once the temperature increase, the viscosity a little bit increase. Okay, that is the difference between fluid and gas in terms of viscosity.